Now we're going to take a look at graphing systems of linear inequalities. We've talked about solving systems of linear equations, and the move to talking about systems of linear inequalities is in order to start looking at questions about optimization. Optimization is an umbrella term for either maximizing something or minimizing something. And in the context of what I'm filming these for right now, we're talking about something like maximizing revenue or maximizing profits or minimizing costs. So here is something without any context. We're supposed to take the system of linear inequalities here. We've got 4 of them. The last 2 are going to trap us in the first quadrant or on the borders of the x-axis and y-axis that are on the edge of the first quadrant. So to graph the first 2, because the numbers are nice, -2 goes into 6, and so does 3 without any remainder. Same with 4 and 3 going into 12. I'm using the intercepts method to do the graphing. So if we put in 0 for y, 3 times 0 is 0. And adding that to -2x would give us -2x. So if we had equals there, -2x equaling 6, divide both sides by -2, would get -3. So -3 comma 0 is our x-intercept. So similarly for the y-intercept, we get 0, 2. And I'm going to graph that here in just a moment. Now, the whether or not it's solid or dashed is depending on whether or not we have an or equal to. And in this case, we do have an or equal to. So it's going to be a solid line. So I have to plot -3, 0 and 0, 2. Connect them with a solid line. And let's see here, from here to here. Notice back here, it's giving us the equation rewritten in slope-intercept form. In other words, y equals 2/3 x plus 2. All right. Now, as for the direction that it would be shaded, because this is diagonal, figuring out which direction the shading is going, what's left or right of this, what's up or down from this, since it's diagonal, that's harder to tell. So you need a test point. And 0, 0, the origin, was not on that line. So if we put in 0, 0, the left-hand side is going to be 0. And we ask, is that less than or equal to 6? And it is. So we shade toward that point. So I can get that showing up here. And with that single linear inequality, that region is unbounded. The definition given in the current textbook being used would say, can we enclose it in a circle or not? And somebody might look at this, because we only see one window at a time, and say, well, yeah, we could. No, actually, you cannot. You keep zooming out, and there's never going to be a circle that's going to cover all of this. So that single inequality, that is unbounded. All right, let's do similar work for the X and Y intercepts of the second line. It also has a or equal to on the inequality symbol. So it's going to be solid. And when we put in 0 for X and 0 for Y, we have 0 less than or equal to 12, which is a true statement. So once again, we will shade towards the origin. All right, so let's take a look at plotting the intercepts, connecting with a solid line, and then getting our shading, 3, 0, and 0, 4. Okay, gonna have to zoom that out to see the 0, 4. There we go. Connecting with the line. There we go. All right, getting our shading, it should be towards the origin. Our inequality, let's see what that was again, just a moment. 4x plus 3y less than or equal to 12. Go. All right, that is still an unbounded region. Then we had our non-negativity constraints or conditions that both X and Y had to be greater than or equal to 0. The graph of X equals 0 is vertical. It would be the y-axis. And since this is X greater than or equal to 0, then because of the or equal to, it's going to be solid. And that's easier to tell which direction to shade that. That's going to go to the right. Y greater than or equal to 0, that would be a horizontal line. It would be the x-axis, also solid because of the or equal to. And because of the greater than part, our shading would be above it. So X greater than or equal to 0. And Y greater than or equal to 0. Now, if we look at the common shading of all of these, that's right here. Let me put that in a different color if I can. Let's see here. Well, let me do this first of all. All right, I've changed the colors here. The first inequality is in blue, and you can see it shading. The colors mixing makes it a little difficult, but down here, we see this blue shading. The second inequality in red, we can see it shading over here, whereas up here, it's a little tougher to tell. We get this mixture of colors. X greater than or equal to 0 in yellow, and then in green, Y greater than or equal to 0. Where those 4 intersections are meeting is showing up kind of brownish. I'm going to try to put something around this here, if I can. I calculated where that point of intersection is, but for right now, that's not important. Let's see. I want to show that we have a bounded region here. All right, here we go. The region we're looking at is made up with vertices, corner points. Those 4 points. Do not confuse the fact that we've got one of the lines intercepts as one of our vertices, but there are 2 others here in this case that are not involved. They're not part of that region. That brownish overlap, because of the mixture of colors, that's our region. And we can see that it is bounded because we can put a circle around it. Doesn't matter where it's centered. And the radius, certain radii would not be enough, like that one right there, but I have it enclosed by a circle right there. So I've shown that the intersection of all 4 of those linear inequalities is bounded.